Okay, so let K be a number field, and X is a projective smooth variety over K. Okay. Then the finiteness conjecture is finiteness conjecture is that the Char group of codimension R is finitely generated Z module. Okay.
Do you consider the case also when R, this group is the group of zero cycles and X is the surface?
I'm sorry? Huh?
Do you also consider the case when X is the surface and R is the dimension of the surface?
Yes, R is an arbitrary integer and X is an arbitrary variety. Okay, projective smooth variety. Okay. Okay. So, for example, if R equals 1, this is okay. Okay. This because this is a model Bay theorem. Namely, if R equals 1, this is divided into the Néron-Severi group and plus Picard group, Picard groups. Okay, and model Bay theorem asserts the finite generation of a Picard group. So this is okay. However, if R equals greater than 2, then it's a widely open problem. Okay. And as far as I know, there's no idea how to attack this problem in case R equals greater than or equal to 2. And as far as I know, even a single example is not known, except the trivial cases. Okay. So this is a very difficult, maybe too difficult conjecture. So we consider a weaker problem. Okay, the conjecture, the finiteness conjecture for torsion. Namely, the Char R, the torsion part. This means the torsion subgroup of Char R X is finite. Okay. If Char R X is a finitely generated Z module, then the torsion part is of course finite. Okay. And then, so in this talk, we only consider the R equals 2, and later we also assume X is a surface. Okay. But anyway, there is a general strategy. To attack finiteness conjecture for torsion. R equals 2. Okay. So let me first explain this strategy. Right. Okay. This is the étale cohomology group, and we define the n H3 of X is the kernel of the map to the function field or total cohomology of function field. Okay. Then this is a theorem of from Bloch-Auger theory. So there is a exact sequence NH3 X DPN2 to tau2 X N. Okay, and the last term denotes the X tau2 such that Pnx equal to 0. Okay, this is bracket Pn denotes the Pn torsion subgroup. And this map is the p-adic regulator. This is the p-adic regulator. So taking the inductive limit for n, we have an exact sequence as a qp over gp to nh3 x qp over gp to tau2 x p infinity 0. Okay, right. So therefore, the finiteness. If we want to show the finiteness of this group, then we have to study the image of p-adic regulator. However, the target space is not easy to compute. So next we consider the QP over the P two. This is in HS3X QP over the P 2, and there is a map. Natural map from H3 of X to the Galois cohomology groups H2 X K bar QP over GP2. Okay.
K the function field?
No, K is a base field.
Or the base field?
Base field. And okay, we assume that K is a K is a number field. Sorry. So, suppose K is a number field. Okay, and that there is a natural map from H3 of X to H1 K. K is a base field to the Galois cohomology group. Okay, and we put the composition by H. Then S Saito and Kanetomo Sato. Okay, so S Saito means Shuji Saito. Okay, so there are many Saitos. Okay, the theorem says H kernel H is finite, and the image H is contained in H1G K H2 X K bar P over the P2. Okay, namely H is almost injective, and the image is contained in the G part by Bloch Kato. Okay. So more or less, this is easier to compute. So therefore, so we have the following proposition. Okay. So if so this is a number field. K is a number field. And then if H1 x K2 QP is surjective onto the G part of K H2 x K bar QP2, then the p primary torsion part is finite. Okay.
Do you prove that that's going to be surjective later?
This one?
Yes.
In general, it's impossible. Okay. The Bloch-Kato conjecture tells that this is bijective. Okay. But neither surjectivity or injectivity was not known in general.
So you don't prove it today?
No, of course. Okay. But this is a general strategy, namely to prove the finiteness of torsion part of the Char group. Then usually we show that the surjectivity of this map. Okay. And I state some known cases.
I have some relevant questions. So if the Bloch-Kato conjecture is true for arbitrary case, then does it imply that all of the Char groups are going to be finite generated group?
No.
If case field is number field?
No, the conclusion is only a finite part.
Okay, or for the torsion part?
Oh, yes.
P torsion part, okay.
Yeah, P primary torsion part.
Okay, I see.
So
See, there are lots of things to do.
right. There's no strategy to show that the finite generation of whole Char group.
Oh, I see.
Okay. So yeah. First of all, if this is a trivial case, if H2 XOX is 0, then this is surjective. And this is a trivial case. And the first non-trivial case was given by Ranga, Shuji Saito. He proved that X is a self-product of elliptic curve, but E is a modular elliptic curve over Q without Cm. Okay. So nowadays we can delete this term, but when they proved that, it was not proved. Okay. The third one. This is due to the Ranga's result. X is a elliptic modular surface. For gamma 4 over Q. Okay. In this case also he showed the surjectivity of this map. And this is Otsubo. He is 1 year younger than I. No, he's the same years old as I, and it's his master's thesis. He proves the same thing, the Fermat surface of the degree 4. And this is a K3 surface. This is a K3 surface. Okay, over Q or Q minus 1. Okay. All right. Okay. So in this talk, we want to consider the same problem when K is a p-adic local field. Okay.
In Lambert's case, is it still open for higher level grade?
I think so. I think so. Yeah, it's a very special case because in the proof he used the fact, for example, x is a K3 and the Picard number is 20 and many other things, or x is covered by. This is the most important fact is x is in this case x is covered by a product of CM elliptic curve. That's a crucial point. Okay, and more or less he reduces his proof to this result. Okay, but this is a without CM, but minor modification. Okay. So anyway, I don't think it is possible to show for arbitrary gamma n, arbitrary level. Okay. Yeah, this is also covered by the self-product of the elliptic curve. Okay. The same strategy. Okay. So now, today we consider the case K is a p-adic local field. Okay. So then the proposition is okay if K is a p-adic field. Okay. So therefore, it's enough to show that the surjectivity of the p-adic regulator in order to obtain the finiteness of the p primary torsion part. Okay. However, a new difficulty appears in this in the local field case. Okay. I will explain it later. Anyway, the question is, okay, tau r x torsion is finite. Okay. At least several years until several years ago, people believed this is true. However, 2007, Rosenshon and Srinivas found a counterexample. So there is a counterexample. Some fourfold x over qp is such that fourfold x tau 3x torsion is infinite. Okay. And independently, Shuji Saito, the same year, Shuji Saito and myself found a counterexample. This is a surface x over qp such that child 2 x torsion is infinite. Okay? So the question is, the answer is no. Okay? Okay. So this is published in the Masanori, and our paper is published in Algebra and Number Theory, Volume 1.
In your case, the surface means n surface?
No, certain surface. And I constructed some hypersurface in P3. Okay. Yeah. And it's not. But this is an important remark. So the above x are not defined over a number field. For example, in our case, x. So x is x. In our case, x is defined by some equation of x is defined by homogeneous equations, but AI is not a number, algebraic number, contains many transcendental parameters. Okay, so x is not defined over a number field, and the proof in the proof. So this fact is crucial. So the revised question is revised. So assume that x is defined over a number field. X is namely x is there is some variety over number field, and k is a number field. K is a number field. Q number field, and large K is a p-adic local field. Okay, so then child R x torsion is finite. Okay. And I'm not sure this is true in general or not. Okay. Maybe nobody is sure this question is true or not. Okay. And as far as I know, even a single example was not known, except a trivial case. Okay. The main theorem of this talk is we found a non-trivial example to this question. Okay, so let be elliptic K3 over QP such that the general fiber is an elliptic curve defined by equation 4 to 4 square equal to 0. Okay. So then tau 2x p primary torsion is finite. Okay.
Do you actually prove that the p-adic regulator is surjective?
Yes. More precisely, we can prove that K2 is G. Okay. Right. Okay. This is the main. Okay. Right. So I think this is a first example to the revised question. Non-trivial example. Okay. Okay. Then I explain a sketch of proof. So for a moment, x, no, okay, no. Okay. For a moment, let x be a projective smooth variety or surface over K and with good reduction. Then we want to show that H1K2 tensor QP is on to the G part. Okay. Okay. But so this cohomology groups decomposes into a Néron-Severi group and its orthogonal complement. Okay. No. Tensor QP1. Okay. G. The decomposable subgroup factors through the subgroup coefficient Néron-Severi. Okay. And it's easy to show that this is surjective. It's easy. Because this is almost equal to the QP product of QP1, and in this case, by the Kummer theory, the cohomology group is almost equal to the multiplicative group of K. So it's easy to find the element goes to K cross. Okay? So this is easy to. This is one to show that this surjectivity. Okay, but this part is easy. Okay? So we put the quotient H2 modulo Néron-Severi. Okay. So we want to show that we show that H1x K2 indecomposable is on to the H1G KV. Okay. Okay. So Bloch Kato introduced a G part of geometric part of Galois cohomology groups together with a finite part of Galois cohomology group. Okay. And so roughly speaking, the finite part is corresponding to the cohomology groups over the SRGP and the model of integer ring. Okay, so this is a smooth model over the integer ring. Okay. So to show the surjectivity of this map, it's enough to show that the H1 xk2 composable tensor QP is surjective onto H1F and H1 xdp k2 surjective onto H1F. Okay. 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 And all right. Okay. Now put the rho x a Picard number of xk bar and rho y be a Picard number of the special fiber, melon 7 yk bar. This is a special fiber. Okay. Then want to check that H1G over H1F and H1G over F. Okay. Okay. Dimension is follows K QP times H11 plus H02 minus rho x. Okay. And this dimension is rho y minus rho x. Okay.
Where is the process of the sign?
I'm sorry?
Okay.
Huh?
No.
Hmm?
The last process. That's okay.
Okay. Okay. Right. So this is a case of p-adic local field case. And if K is a number field, then the dimension of H1F is H11 plus times K Q, no, plus my rho x times R1 plus R2 and R1 plus R2. maybe R1 plus R2. Okay, and this is usually infinite. Okay. So I explain. What is the new difficulty in the local field situation? Okay. So the known case is 2, 3, 2 to 4. In this case, the f part is 0. Okay. This number becomes 0.
What's the case?
Known cases, Ranga Saito, Ranga, and Otsubo. And the crucial point in their proofs is to attack this part. Okay, but it was done by using the Flach's element. Okay, this part was spanned by the Flach's element. Okay, so that's their proofs. Okay, but in our case, K is a p-adic local field. So then H11 is greater than or equal to rho x. So if PG is not 0, then this is always positive. Okay. So we have to attack H1G modulo H1F together with H1F. Okay. This is non-trivial. This can be non-trivial. So this is a new difficulty. Okay. In fact, let x as in cell, then H11 is 20, H02 equals 1, and rho x is 20, and rho y is 21 or 22. It depends on the choice of p. Okay. So therefore, the dimension of H1F K equal, in this case QP, V is 1, and the dimension of H1G modulo H1F is 1 or 2. Okay. So therefore, we have to attack this part together with this part. Okay. And 2. Okay. So this is a 1 or 2 dimension, and this is a 1 dimension. And the proof to find the element which spans this space is the same as their proof. Okay. Namely, I use a Flach's element. So I don't tell it, but this is a new result. So I'd like to tell the proof. Okay. So I want to show that. So there exists Xc H1x K2 such that rho Xc Zp integral model P such that is not 0 in H1FKV because this is one dimensional. So this implies the surjectivity. Okay. Now remember the lemma which I told yesterday. So if Xi satisfies the following. So first one, the log C is not 0 in H1 and K, H2, X, K bar, QP2, and let CI is a generators of Néron-Severi groups. Then, and Fy is a composition of H1K2 to H1 Ci tilde K2 to QP bar cross. Then Xi satisfies Fi Xi equal 1 for all I. Then log C is not 0 in H1 K V. Okay. So we will find elements satisfies the condition 1 and 2. Okay. Okay. Now the X is an elliptic surface over P1, and the singular fiber is as follows. First of all, singular fiber over T equals 0, and the component is 12, I12, I12, and T equals plus minus 1 or plus minus I, and there is the I1, the singular fibers. And over the infinity, the additive fiber, non-multiplicative fiber. So-called 4 star. Okay. Now we consider the multiplicative fiber, D1 over 1 and minus 1. Okay. So therefore, there is a corresponding element in H1K2. H1K2 as a Cook C2. Okay. And put C is a C1 minus C2. Okay. Then one can check that the second condition are satisfied. So 2 is satisfied. So therefore, the final step is the non-vanishing of p-adic regulator. Then we use the main theorem, which I told yesterday. Okay. So namely, the non-vanishing is equivalent to the C does not contain in the 2 UK bar QP to G, or in this case QP, K equal QP. Okay. And yeah, okay. So U is X minus D1 plus D2. Okay. But the main theorem yesterday tells that dimension of H2 UQP bar QP2 GK less than or equal to dimension of FP phi X, Z, P, D, Z, P, F, P. Okay. And direct calculation, one can show that this is 0. This is a direct calculation. If P equal 7, 11, 19, 23, 31. Okay. So therefore we have no vanishing for these primes. Okay. Now I forget. So I'm sorry. So in the theorem, I forgot to assume that P is only only finitely many P's. Okay. Theorem. So add in theorem add the assumption. Okay. So I'm sorry. Yeah. First of all, P is equal to 3 mod 4. Okay. And I don't know. So I cannot answer your question exactly because I don't understand why only in this case does not this dimension vanishes. Okay. Anyway, in this case, X is a supersingular. So I think this is this causes the vanishing of this space, I guess, but I don't understand it well. Okay. Right. Okay. Yeah, maybe.
Do you have some expectations about what will happen for bigger primes?
Yeah, I think only in this case we have the vanishing here, and I think, I guess, if P is model P is 1 mod 4, then I think this is but I don't know. It's a very mysterious fact. Okay, maybe I stop here.